Now let's see electric field of an electric dipole. You can see here is the electric field of an dipole. The electric field near a dipole is not zero. The reason is simple, because both the charges are having some separation distance between them. They are not overlapping each other. That's why the electric field is not zero near the dipole. However, if you go far away, means if the distance r is quite larger than 2a, then in that case the electric field of positive and negative charge will be nearly same, and that's why the electric field far from the dipole will be nearly zero. The electric field of a dipole falls rapidly with distance, because the electric field of a dipole is E proportional to 1 upon r cube. Why it is so, that we will learn later. That's why the electric field decreases very fast as the distance increases. The net electric field is always a vector sum of the electric field of positive q and negative q at any point. Whatever point you choose, suppose if you choose this point, then at this point the electric field of this positive q and negative q will be superimposed as per the superposition principle. So it will be a vector sum of both the electric fields. We are going to find out electric field of a dipole on its axis and on its equatorial plane. Let us see what is an axis of a dipole. A line joining the two charges of electric dipole is known as axis of the dipole. You can see this line is joining both the charges plus q and minus q. That's why this line is known as axis of a dipole. Now let us see equatorial plane of a dipole. A plane perpendicular to the dipole passing through the center of the dipole is known as equatorial plane. A plane which is passing through the center and is perpendicular to the dipole itself, that is known as an equatorial plane. So this is equatorial plane, and a line on the equatorial plane perpendicular to the axis is known as equator. Now first we will find electric field on the axis of a dipole. Here you can see this is positive q charge and negative q charge. So this line becomes the axis of the dipole. So first let us choose a point A. Here a point A is shown, which is at a distance r from the center of the dipole. This is point A and this is the center of the dipole, and this is the distance r. Here we will find out the electric field. Obviously at this point the electric field will be due to positive charge and negative charge both. Now due to positive q charge, the electric field at this point A will be radially outward. So this is the electric field E positive q, and due to negative q charge, the electric field at this point A will be radially inside, means towards the charge. So this is the electric field E negative q. Now we know that electric field of a point like charge is E is equal to 1 upon 4 pi epsilon 0 and q upon r square, where r is the distance between charge and the point. Now if we talk about this positive q charge, then the distance will be this much, which is r minus a. You can see this is r and this will be a, that's why this distance is r minus a. Whereas the distance of negative q charge from the point will be equal to r plus a. So this distance is r plus a. According to that, the electric field of positive q charge, that is E positive q, will be q upon 4 pi epsilon 0 r minus a whole square caret p, and for the negative charge it will be E negative q minus q upon 4 pi epsilon 0 r plus A whole square caret P. Here this caret P is the unit vector in the direction of dipole moment. So we can understand this E positive Q is in the direction of caret P and E negative Q is in opposite direction of caret P. We can see this is E positive Q which is in the direction of caret P and E negative Q is in opposite direction of caret P. So the total electric field at point A on the axis will be E is equal to E positive Q plus E negative Q. Here you can take out Q upon 4 pi epsilon 0 as common. So the remaining term will be 1 upon R minus A whole square minus 1 upon R plus A whole square caret P. Now if we solve this bracket, we will get 4AR upon R square minus A square whole square. So the electric field equation becomes E is equal to Q upon 4 pi epsilon 0 4AR upon R square minus A square whole square caret P. At a very large distance from the dipole, that means R is very greater than A, this term can be written as R square because R is very greater than A, so we can ignore this term A square. So the remaining will be R square raised to square, that means R raised to 4, and here one R is also there. That's why the remaining term in denominator will be R cube. So finally the electric field on the axis of a dipole at a very far distance will be E is equal to 4QA upon 4 pi epsilon 0 R cube caret P. Now let us find electric field on the equatorial plane. You can see here is the dipole and here is the equatorial plane of the dipole, which is perpendicular to the dipole and passing through the center. We will choose a point B on the equatorial plane at a distance r from the center. Here is the distance r from the center of point B. Now the magnitude of electric field at this point due to positive Q charge and negative Q charge can be written by these equations. Let me clarify one thing. This distance is r and this is a. So obviously this will become r square plus a square. Now for both the charges, for negative Q charge also this is r and a, so this becomes r square plus a square. That's why the electric field due to positive Q charge will be equal to EQ is equal to Q upon 4 pi epsilon 0 1 upon r square plus a square, as well as for negative Q charge it will be E negative Q is equal to Q upon 4 pi epsilon 0 1 upon r square plus a square. You can see both of these equations are same. That means magnitude of electric field at this point will be same due to positive Q and negative Q charge. The directions of this electric field E positive Q and E negative Q are shown in the figure. Here this is positive Q charge, so the electric field at B point will be radially outside, and this is negative Q charge, so electric field due to that will be radially inside, means towards the charge. Now if we consider the components of this electric field, then this E positive Q electric field will have two components. One will be parallel to the dipole and one will be perpendicular to the dipole. The same way, two components of this E negative Q will be one in parallel to the dipole and one in perpendicular direction of the dipole. In this case, the components which are normal to the dipole will be cancelled out. Here you can understand one component of E positive Q and another of E negative Q, both which are perpendicular to the dipole, are having same magnitude and opposite direction. So they both will be just cancelled out. We can understand The remaining electric field at point B is the addition of these two components of the electric field produced by plus Q and minus Q. And so the resultant electric field will be in this direction, which is opposite to the dipole moment. Now these components of electric field will be E positive cos theta and E negative cos theta, because this angle is theta. So this two angle will be also theta. That's why the component of E positive Q in this direction will be E positive Q cos theta, and the component of E negative Q in this direction will be again E negative Q cos theta. So finally the electric field at point B will be equal to E is equal to minus E positive Q E negative Q cos theta caret P. Here you can see this is a minus sign because the direction of this resultant electric field is opposite to the dipole moment P. Now putting the equations of E positive Q, E negative Q and cos theta, we will get this equation. Let me clarify that cos theta will be A upon under root of R square plus A square. This is because here is a right angle triangle and this is angle theta. This is R and here is A. So this becomes under root of R square plus A square. So cos theta becomes A upon under root of R square plus A square. So this is cos theta is equal to A upon under root of R square plus A square. So finally the electric field becomes E is equal to minus 2qa upon 4 pi epsilon 0 R square plus A square raised to 3 by 2 caret P. At a large distance, that is R is very greater than A, the same equation now can be written as E is equal to minus 2qa upon 4 pi epsilon 0 R cube caret P. Here we are getting R cube because R is very greater than A. So in the previous equation, here in this term we can replace this R square plus A square by putting just R square. So this is R square raised to 3 by 2, that becomes R cube. So we are having R cube here. Now the electric dipole moment vector P is 2aq caret P, and we are having this term in both of the equations of electric field on the axis and electric field on the equatorial plane. So we can replace this term by putting vector P there. Let me show you the electric field equation on the axis. Here we are having E is equal to 4qa caret P, which can be replaced by putting 2 vector P. So we can write now the electric field at a point on the dipole axis, that is E is equal to 2 vector P upon 4 pi epsilon 0 R cube. The same way in the equation of equatorial plane we are having 2qa caret P, which can be replaced by vector P. So the electric field at a point on the equatorial plane is vector E is equal to minus vector P upon 4 pi epsilon 0 R cube. For both of these equations, that is the equation of electric field on the axis of the dipole and the equation of electric field on the equatorial plane of the dipole, we can see one thing, that both are having vector P. But in the first equation we are having 2 vector P. That means the electric field on the axis is double than the electric field on the equatorial plane for the same distance r. I repeat, if the distance r is same, then magnitude wise the electric field on the axis will be double than the electric field on the equatorial plane. One more thing to be noticed, that here in the second equation we are having a negative sign. That means the electric field on the equatorial plane is in negative direction of the dipole moment, whereas the electric field on the axis is in the same direction of the dipole moment. Let us see few important things about this electric field equations. The first is the electric field E is inversely proportional to R cube, that is E is proportional to 1 upon R cube, that you can see here in this equation. For both of these equations we are having R cube in the denominator, that means E is proportional to 1 upon R cube. Therefore, the electric field decreases rapidly with the distance. The second point is, if the point is neither on the axis nor on the equatorial plane, the electric field depends on the angle between the dipole moment P and the position vector R. We have seen electric field on 2 points, that is on axis and on the equatorial plane. But if the point is neither on axis nor on the equatorial plane, then the electric field will also depend on the angle between the dipole moment P and the position vector R. Now let us see a definition of point dipole. A dipole for which the distance 2a approaches to 0 and the charge q approaches to infinity, such dipole is known as point dipole. Obviously, it's an hypothetical dipole. But if we can assume that the distance between two charges is almost 0, and if we can also assume that the charge q is very high, almost approaching to infinity, then such dipole can be called as point dipole. Now the thing is, the equation of electric field of a dipole on the axis and on the equatorial plane gives exact value for point dipole, whereas for any practical dipole, these two equations what we have derived will give approximate values, whereas for point dipole it will give exact value for any of the value of R. Now let us see few molecular dipoles. In most of the molecules, the center of positive charges and the center of negative charges lie at the same place. Therefore, their dipole moment is 0. Obviously, if the center of negative charge and center of positive charge are coinciding on each other, then the distance 2a will become 0, and that's why the dipole moment will be 0. Examples are CO2, carbon dioxide, and CH4, that is methane. Here this is carbon dioxide and this is methane. So for both of these cases, the center of negative charge and positive charge are coinciding. That's why these two molecules are known as non-polar molecules. But some molecules are such where the center of negative charges and the positive charges do not coincide on each other. Therefore, they have a permanent electric dipole moment, and such molecules are called as polar molecules. The examples are H2O, HF and HCl. Here is H2O. We know that the electron negativity of oxygen is more than that of the hydrogen. That's why oxygen becomes negatively charged and hydrogen becomes positively charged, which creates a dipole moment. The same happens in case of HF. Here, the electron negativity of fluorine is more than hydrogen. That's why fluorine becomes negatively charged and hydrogen becomes positively charged, creating a dipole moment. And the same is for HCl2. Here the electron negativity of chlorine is more than that of the hydrogen. That's why chlorine becomes negatively charged and hydrogen becomes positively charged, which creates a dipole moment.